is fixed. We cannot change this. Okay, the outer dimension is fixed. Okay, we cannot change because at the end of the day, when the client measure the part before they pay you money, is they will measure the outer surface radius. Okay, the rest they don't care. I mean, they do care that it does not collapse easily. Okay, so I'm going to do some dimensioning over here. Okay, and then there's a we know that this is our inner surface. They don't really care what this inner surface, as long as the outside shape is there, they're fine. And then this is where okay. So this is our neutral axis. Okay, neutral axis, where what is happened down here, where we have what, where stress is 0. Now you guys will learn this later on in those in mechanical engineering. You will learn this in 2PO4. Okay, so we decided to use, so what is given to us is this dimension. This dimension we cannot change at all, unfortunately. Okay, we have to comply. So this dimension that I'm going to draw for you over here, this dimension over here, okay, cannot be changed, and it's fixed at 0.02 meter fixed. Okay, and as I said, for this case, we can change the thickness of the plate. So we decide, or we try the thickness to be equal to 0.005 meters. Okay, we make that plate thickness. Okay, so we know to the neutral axis, right? We know this dimension then. Our neutral axis, and then our ID. Okay, so our neutral axis, this is at 0.0175 meters, and the internal radius is 0.015, right? Okay. So we're going to do a very simplified version of the strain induced. Okay. As I say, if you refer to this diagram, we have to limit the plastic strain to 0.1 to 0.2. More than that, it's going to get more difficult. Okay, and we have to know how difficult it can get. Okay, so as I said, thickness is something that we can change. Okay, but up to a certain, you cannot make it too thin where this part will crumple. Okay, we can't do that. There's a limit. There's a lower limit. Okay. So when we start working on this material, they did not know how this material behave. I gave a course exactly like what I'm doing to you guys now. Okay, I explained to them what TRIP 800 is all about. Then I explained to them how to design a part with it. Okay. So the benefit of knowledge like this is time to market. If you know knowledge like this, later on you'll see, we can design a product that's easy to manufacture. That's why it's called design or for manufacture, right? So we're going to do, we're going to calculate, right? We're going to calculate the plastic strain induced, okay, on the material or in the material with or when the plate thickness is at 0.005 meters. Okay, so we change. So Cn, where you see down here the Cn, okay, is the original length of material. Okay, it has zero stress before and after manufacturing. Okay, so that's why we call it what? The neutral axis. Okay, so zero stress. Why is it zero stress? So zero stress is because there is no change in length or circumference after deformation. Okay, so Cn, so when you bend, right? So this circumference, okay, and Cn, the distance are the same. Okay, so now we calculate Cn. Okay, we calculate Cn. So Cn, very simple formula, is equal to half pi times by the radius. Okay, so the neutral axis is 0.0175. So this happened to be equal to 0.0274. Okay. Then we are going to calculate C naught. C naught. So C naught is the circumference. Okay, C naught is the circumference of the outer surface. Okay, so C naught is equal to half pi 0.02. Okay, 0.02. So this happened to be 0.0314. Then we also calculate Ci. Okay, so circumference of the inner surface. Right, so this happened to be also equal to half pi 0.015, and this is equal to 0.0234. Okay, so what this means, again, this is a simplified calculation. Okay, so what this means is if this is the length of our C naught or Cn, C naught will be longer, Cn or Ci will be, okay, so let me write over the other side. In terms of length, okay, so this is your Cn, C naught, and C internal. So this is our delta. Right, our delta. So we calculate our delta. Okay, so C naught minus by Cn. Okay, so this will be equal to 4 positive 4 times 10 to the power minus 3 is the same as C internal minus by C neutral is equal to minus 4 times 10 to the minus 3. Right. So this is in meters. So positive means this is in tension. Right, that's in tensile. This one is in compression. So we calculate the strain. Okay, so the change in length divided by the original length, right? Or circumference, or delta C divided by C naught. So this is equal to plus or minus 4 times 10 to the power minus 3 divided by 0.0274. So now the value we get is plus or minus 0.146. Okay. So this is the strain, the strain that we induce. Okay, based on the dimension over here. So now, what if we were to reselect? Okay, so this is for the thickness is 0.005 meters. Okay. Now, what if we were to reselect the thickness? So we carry out the same calculation. Okay, now we change the thickness to thickness of the plate to 0.003 meters. Okay, so we calculate the same thing, right? We calculate the same thing. The new Cn, then the neutral will be half multiplied by pi multiplied by 0.02 minus by 0.003 divided by 2. So this will be equal to 0.02906. Why I use this number? Because this 0.02 is fixed. We cannot change this one. Okay, we cannot change that one, unfortunately. Okay, so our delta C now, our change in circumference is equal to 0.0314 minus by 0.02906. Okay, I'm going to see there if I have some question. 0.146. 0.146 is a strain. It's not the change. Okay, it's a strain induced.
What's the 0.005 thickness underneath